In today's lecture, we're going to explore together the landscape of generative graph neural networks. So this is a roadmap to a diverse pool of generative models with application to graphs. So we will look at the taxonomy of graph neural networks, and we'll have a few examples. So if you guys want to develop your knowledge at a deeper level, on graph neural networks and their generative power, we would dedicate, I would say, a full course to this. So this is really a very rich and heavy research field. So today I'm just giving you a snapshot of the field, and not the whole of it, but bits of it. Okay, cool. So let's get started with the first part, where I remind you of what we have done so far. So previously, we have looked at primarily the power of GNNs in classifying data and regressing data. So we looked at predicting labels, predicting scores. We looked also at, like during this, supervised classification or learning process, we learned how to embed graphs, how to discover patterns in graphs, and how to do aggregation, transformation. So we've seen different operations that we use to classify or regress graphs. So we have primarily focused on supervised learning, and such as node classification and graph classification. For example, here we have an input graph G, let's call it, for example, right? And if we input a G to F is our neural network. So this is the GNN neural network mapping function from, like the whole mapping function from the first layer to the very last layer. So that's the, global mapping function. This will give us an output label Y, okay? So this is for our graph. And this is the predicted Y, so let's put it like here. And ideally, we would want it to be close to the ground truth. So this is a classification task. It's supervised, so we learn how to predict labels. We have also seen the example where we're predicting multiple output scores. So we have seen multiple multivariate regression. And here you can see that we have many scores to predict. So for example, for this brain, we want to predict the age of the brain. We want to predict also the sex, whether it's a brain of a female or a male. And we can also predict many other, many other scores related to the health of the brain or the state of the brain, okay? So given this brain, we feed it into a graph neural network, and we are able to predict all these scores together. So far, this has been a very exciting journey. We have covered different aspects, different properties, including, for example, the invariance, equivariance, and expressiveness in the previous lecture. And today, we're going to look at the second aim, one of the main aims of GNNs. Where can we use GNNs? So we can use GNNs to learn the distribution of given graphs. Okay, so we want to learn the distribution of given graphs, and by learning the distribution of the real graphs, for example, the brain graphs, right? How the brain graphs are, from which distribution they are drawn from. If we can approximate that, then we can easily learn how to generate more novel graphs. So for example, generate a target graph P from a graph A, and we're going to look at different examples, or a few examples, I would say, today, okay? So here, in this example, we have a source graph. So let's say the distribution of, as you guys know, this graph doesn't have any node features. So we don't have any node features here. Still, we have the topology. So what we can do, we can plot the connectivity weight, the weight or the distribution of these edges. So if it's a weighted graph, so we can have, for example, so let's say the source graph will have this kind of distribution, right? So here, and then the target graph domain will have a different distribution, all right? And our goal is actually, if we want to generate in this domain, if we want to generate data, so we want to generate data in the target domain, right? Given the source, given F source, so given FG source, we want to predict this graph, which is a G target. Okay, so this is our prediction, and ideally, in a supervised framework here, if we have the ground truth of the target, we can calculate the distance between these two and see whether we have the same topology or not. So we can evaluate the correctness of our prediction. So let's say this is the distribution of the ground truth data. So this is the distribution of the target data, okay? And then if we do our prediction and we have a good approximation of this distribution, so maybe we will mimic it a little bit. So we'll have an approximation that looks like this maybe, okay? So this is not too bad, actually. This is very close to the ground truth distribution, and this is what our model has learned. So our model has learned how to generate samples that fall, under this distribution. All right, cool. So now this is one. I know it's a simple example, but we will dig a bit deeper later, and we'll look at how we do the generation using different tactics and different approaches. Okay, so first let's start with the supervised generative GNN tasks. And here, of course, supervised means that we do have the target graph, okay? So we know that this graph here corresponds to the source graph, which is in the input space. So we have two spaces here. We have the input space. Let's write it down. So here we have the input space, okay? So the input, let's call it domain. And we have the target domain. So domain, okay? So if we don't have the corresponding graph here, we don't have a ground truth, then we move from supervised to unsupervised or self-supervised, and we will see a few examples later, okay? So now this is a generic task. So which means what do we have here? So we have first our input graph. So this is the input graph. And the input graph has the A matrix, so of size n by n, so it's the size of the input. We have here n nodes, the feature matrix, which has here the dimension of n input, the input feature dimension, for example, D, okay? And then we have also graph edges. So here we stack all the graph edges. So E11, E12. So for example, let me write it down. So just for clarity, so E11, so this is self-connection. We can do E12, E13, etc. And then for each one, right? So we're going to put the features of that edge. Okay, so this is the feature, the features or the attributes of edge, for example, Aij. And you can see them here. So these are basically edge attributes, and we have node attributes in pink color. All right. Now, there is one thing I want to point out before we go we explore the target domain, which is like what we want to generate or what we want to predict in the target domain given the input graph, right? So one way of representing the E is to basically represent it as a tensor. So we have, for example, here, this vector, okay, is if we have nodes I and j, so as row and column, and we pick this value. So the vector that we read along this edge feature dimension is the same as this one. So these are exactly the same. So what we have done here is basically we flattened the tensor, the edge attribute tensor. So there are two different representations that we can use for the edge attribute. So some papers or some, I would say formalization, mathematical formalization, they use the tensor, and others they flatten it for to make it easier to do computations and matrix to matrix multiplications. Okay. So now what do we have here? So we have an input, the input graph, and our goal is to predict the output graph. So the output graph, you guys, if you guys know this, here we have more nodes. Of course, we can have less nodes, all right? So you may want to grow a graph, you may want to shrink a graph. These two graphs could be completely different, which means this graph is drawn from domain, A, and this is in domain B, which means maybe the nodes are not in correspondence. Maybe here I have a yellow node or an orange node, and this node has no match. in the source domain. So basically, we may have completely unmatched graphs. We may have also, some graphs, that grow, which means all these nodes will exist in the target domain, and I'm just, for example, growing my graph. Okay, so something like that. So you guys can see that there are different scenarios, and you don't have to have matching or parity between these nodes. You can take GraphVAE and in a very generic way, try to predict a different GraphVAE with different nodes and different edge types and different feature types. So here, basically, this is the generic formalization. So given all of these three elements, okay, ideally, this is a graph with all the annotations, right? We want to predict the target graph with n prime nodes and also a different dimension. The dimension here could be different, okay? So we may have more or less features in the target graph, right? And then also we may have a varying size or a different number of edge features for the target graph G prime. So here, basically, if we write it mathematically, what are we trying to do is we are trying to learn a mapping or a neural network, an FGNN, or a neural network here that takes as input A, X, and E, and it outputs a prime tilde prediction, X tilde, and let's write it down, and E tilde, prime tilde, okay? So these are our predictions here, and let me just put it over here. So this is our network, and how do we know that our network, has performed well? So of course, if we do have the ground truth, we can easily do pairwise comparison. We compare the predicted A with the ground truth one, the feature map, the node feature map, and the edge feature map with the ground truth that we have. Okay, so supposedly we do have these here because we're doing a supervised task in this example. Okay, now let me ask you a question. So for example, so how to define the loss function? So I just gave you some hints here. So how to define the loss function, the generative loss function. So this depends on the target data to generate. So we need to first fix or identify which data do we want to generate. So do we want to generate only the A? We don't care about the features. Do we want to generate the topology, the graph topology, the A matrix, and the features assigned to the nodes? So we have a ground truth feature that we want to benchmark against. So we need to select which variables, which graph variables we want to optimize over, and these will define what we want to generate, okay? So remember, so one thing that is, so this is a very important rule. I want you guys to remember that, if we want to use a GCN, right? So message passing requires two things. It requires the A, the topology, and the features, because we were learning how to embed each node. So that's the power of message passing, or the update rule in GNNs is to learn how to embed nodes and whole graphs also. So we actually need these two if we want to do GNNs, okay? So the E is additional, but primarily we need A and X, which is the initial embedding that we initialize. So X is the original features, okay? So now I have a question here. How to solve the following generative task? So given that we need both, right? Okay. How to solve this generative task? So the generative task here is that we have a source graph, okay? So, and this source graph is not annotated. So we have only the topology. So this is basically, if you draw the matrix, it's a 4x4 matrix, okay? And then we have here a bigger matrix. So here it's 6x6. Oops. So we have 6x6 matrix, and what we want actually to predict these, to map, the small matrix onto the bigger one, right? So we want to predict these values. So this is, let's call it the low resolution graph, AL, for example, okay? And this is the high resolution graph, and we want to learn this mapping here. So we don't have actually any features. We only have the A's, okay? So now, how can we do that? This is something I want you guys to take a minute and think about it. how can we leverage a GCN and do this predictive task using GCNs, knowing that we don't have any features? So which kind of tricks or strategies we can use to do this? So here we have different solutions. So let's look at that. So first, all right. So if we don't have any features, what we can do is we can initialize, we can create features. So if our target is to generate a graph that has only adjacency matrix, we can initialize X either randomly. So what we can do, we can take all these values and draw from a normal distribution, for example, okay, and 0, 1. And we can put different values here. So 0.3, 8, 1, 0, etc. All right, so we randomly sample. The second option is we can use the topological attributes, which would may be more interesting of each given node. So for example, here for each, so here we can do topological attributes, topological or centrality attributes, measures, okay? So for example, we can take the node degree here. The degree is 2. So we can take the degree of the node. We can also put different values here. So these values will be different topological measures, like, for example, rank page. We can do eigenvector centrality, right? We can select different or clustering coefficient to detect segregation properties in a network. So there are many attributes that we can derive from the graph itself, from the topology itself. So this is, topology driven, okay? Topology driven. Now, the last one is to use identity. We can, this is also another option. You may have other options depending on the problem and on the data. So we can basically simply set them all to 1, okay? So we have a bunch of 1s for everyone, for the source network and also for the target, so for the target network. And here, this is just, I want you to keep in mind, guys, that this is just an initialization, okay? So we just initialize. Now, what we're going to do, these, because we're optimizing over the target graph, so this is our target graph, we optimize over the target graph loss. So we want the A basically. So let's look at our loss here. So what we want is actually, we want to minimize the distance between the ground truth, graph and the target domain. Okay, this is the target graph A prime. And so this is the ground truth and this is the prediction. Okay, prediction. So this is the prediction that we have. And what we want to do, we want to minimize the loss. So this is our GNN loss. We minimize over the distance between these two. Now, for the GNN mapping, we want to learn a network function f, or GNN, that takes as input A and X. So we need to give it the X, okay, in message passing, for example, if we're using GCNs, okay? And then we are predicting these two. So although we're going to predict the X tilde prime, so we will predict these values. So I'll talk about it in a second. We don't need to evaluate this. We don't need the loss, okay, to include this. Why? Because we don't have ground truth features. So no ground truth X. Okay, so X prime, we don't have ground truth X prime. So basically what we need to minimize, although our network will learn these, okay? So when we minimize, when we optimize this task, when we try to generate this graph, so what our network will do is that it will learn these embeddings. So remember, guys, we do the update of the embeddings H in each layer K, right? And this is in the target graph. So we know already that we have 6 nodes. So all we need to do is basically to learn the embeddings of these nodes and as in the target domain. And if I learn the embedding at layer K, okay, so this is node, for example, let's write of node I, and this is the embedding at layer K of node J. So what we can do to predict if there's an edge here or not between them, we can use the sigmoid function of HK of J transpose HK of I, and this will give us the probability of an edge existing or not existing. Okay, so this is a link prediction kind of problem, and the goal is actually to learn very good embeddings. If we learn good embeddings, then we are able to predict if there is an edge or not, and we can also basically quantify that depending on if we have weighted graphs or we have binary graphs, of course. But the key idea is to leverage these two embeddings that we're learning through the GCN and the target domain, the target graph, and to derive the connections, to derive the A matrix, so the A prime matrix. Okay, so this will give us the A prime matrix that we want to predict. All right, cool. So now this is why it's important to learn these embeddings. However, we're not evaluating the features, these embeddings, or we're not reconstructing any original features in the target domain because we don't have them actually. Okay, so now here in the loss function, so we're optimizing the loss. So as we optimize the loss, what happens is that you predict better the graph. So you have the number of epochs here, and you're training your loss L1. And if we have, for example, a graph like this, so let's say this is the target graph, and the graph we're look at, let's say, so this is, for example, the ground truth graph duplicate. So we want to converge to this one. So as we optimize, as we minimize our loss, okay, here the loss, of course, has the parameters of theta that parameterize this whole network. So this stacks all parameters, all GNN parameters, okay? And as we optimize, basically what happens is that at the beginning, we're going to have really bad kind of predictions. So we may have some mistakes here made, and the prediction is not actually good. And then as we progress, the prediction becomes better, which means during the training graph at epoch, for example, I don't know, K epoch here in the final one, training, this is a training graph, final epoch, okay, will become better. So we are optimizing over, of course, the train set, and this been optimized over the train sets. And we know that already, okay, the train set. So we need to optimize over the train set, the training graphs. All right, now the second question, the second scenario is when we have a graph. The graph has only node features. So now we do have the ground truth node features, and we want to predict the topology. Additionally, we want to predict these node features. So this is a more complex problem because now we want to learn how to predict the topology itself based on embeddings, but we also want to recover some node features. So these are not, necessarily the embedding. So imagine that we have the original feature vector here, the source graph feature vector. So sometimes we need to kind of decrease the dimensionality, but at some point you need to increase it if you have maybe way more features in the target domain. So if this guy right here has many features, we need to somehow upsample, right? So as we do in simple deep learning models. Okay, so we need to do some upsampling. But anyway, so this is a complex problem. We're not going to cover different approaches, but I want you guys to engage in thinking about these problems. So how can we solve them? And given the tools that you learned during this course, you should be able to at least formalize the first kind of steps of a plausible solution to this problem. Okay, so first here, what we have our GNN mapping function. So the GNN mapping function takes as input A and X, and outputs, the predicted A prime and the predicted X prime tilde. And the loss now has two terms. So we need to optimize over two things, right? So we have the input, we need to somehow calculate a distance. So this distance could be any kind of function that we're using, right? It could be L1 norm if we want to impose sparsity. So it could be L2 norm. It could be L1 norm if we want to impose, sparsity. So we want to learn, we want our matrices to be sparse. If we add also regularization, of course, we want to sparsify them, but this means that we're using different distances. We can use different types of distances to compare, the similarity between A prime and the predicate A prime tilde. All right, and then we do the same for these. So we want to compare how close these are, and this will define our loss that we want to optimize. Now, the third scenario is when we have when the target graph has actually both node and edge features. So we want to generate an adjacency matrix and also its node and edge matrices in the target domain. So here, for example, this is, our mapping network. So the network is huge. Actually, it is able to predict three things, the whole graph topology, the features assigned to each node in the target domain, and the edge features in the target domain. Okay, so the loss function now is even bigger because we have three terms, L3. So here we have the first term that evaluates, so maybe we can write it down. So this evaluates the graph topology, topological soundness. This evaluates the quality of the features, the node features that we predicted. And this evaluates the edge features that we predicted. Okay, sorry, edge features. Okay, so now lambda 1 and lambda 2, these are scalars. So these are, they kind of, balance these terms. So for example, if the range of this distance is in the order of 100 and the range of this distance is in the order of 1, so you guys can see that lambda 2, to bring these two together, right, to the same range for the optimizer, we need to multiply by 100, because if you don't do that, the optimizer will only focus on the largest value, which is of the order of 100. So all these values are very large. The loss is so large, and this term is negligible compared to the first term. So to kind of, counter that, we add a lambda here, lambda 2 scalar, and we can set lambda 2 to 100, so we can balance things out. And this means terms out. And this means basically that we want to optimize these two equally or in the same way. All right. So we want to optimize them equally or in the same way. And if we don't want to do that, if we want to pay more attention to this guy, so maybe we can multiply by 50. So we can set, this will give less attention to this term. Okay, in the optimization. So we want to actually minimize the first loss compared to this one. So this is, the logic behind these values, or like these parameters, hyperparameters that we need to tune. And depending on the problem and depending on the focus of the optimizer that we want to have. Okay, cool. So now there are various supervised or conditional generative GNN tasks, so supervised or conditioned on the target graph that we want to generate, because we do have a ground truth. So sometimes we can use the word conditional here. It has different usages. Conditioning means on a label, on a context. So you have a variety of usages or applications of word and formalization of conditioning in generative learning. But here we will use it just, in a simple and reductionist way. We say like, supervised is a type of conditioning. Okay, so which means we condition on the target that we want to predict. So so there are different tasks. So if you want to generalize, so this is also from a review paper. So if we want to predict a single graph and the nodes are the same, so they have the same meaning here, so which means we're only doing rewiring. So you only simply rewire. So this is a rewiring problem, so which means rewiring and reweighting. Okay, so you weight the edges. So you can see this one has become thinner in the target domain, for example. Okay, and you can also add a new graph, so a new edge. So here you added a new edge. So that's kind of rewiring and also adding more. So you can change edges, rewire, but you can also add edges. So it's more complex and more rich than simply changing the edge connectivity. Okay, so now this is one problem here. We can of course add features and we can add edge attributes. Okay, so here it's only topology. So now in this example, in the multi-graph prediction, we have given a source graph our goal is to generate multiple graphs jointly at the same time. So the target domain has multiple types of graphs to generate. So for example, given a brain graph here that shows morphological connections in the brain between two parts in the brain or two nodes in the brain, we can predict, for example, the functional connection, which is a different type of connection, okay? So in the structural one, also another type. So these edge values, the meaning of the edges here will be different, okay? So we won't have the same meaning of the edge here across these domains, right? Across these target domains. So generative GNN dimensions basically we have seen, here we're doing different domains, right? So this is the first axis. We can also do different scales, and you can have a generative model that solves all of these together. So which means it does multiple scales, multiple domains, etc. So here, for the sake of simplicity, we kind of, categorize them into different subcategories. So here, for example, we have a low resolution graph. It means it has a number of nodes n, and then we want to predict a graph in the target domain n prime, and n prime is much larger than n, okay? So this is what we call the graph super resolution. So you're trying to create a bigger graph from a smaller one, and this is not just growing the graph. These nodes may not have correspondence. So if you look at these two nodes, right, there is no matching. This node doesn't exist in the original graph. So we're generating completely a bigger graph in the target domain from a source graph, and there is not necessarily a matching or correspondence between them. Also, the meaning of the edges here will be different. So the meaning of this edge and the meaning of that edge, like one would, for example, quantify a sort of a similarity in a particular property, and the other one will capture a completely different property, okay? So now the last one is graph evolution prediction. So this is across time. So here the example I've given is on the brain graph. So we can also apply it to any kind of graphs. So this means that given a source graph, we aim to generate its time-dependent evolution over time at different time points. So our goal is to actually learn a time-dependent, GNN, time dependent mapping, GNN, that allows us to predict these at different time points, okay, in the future. So this is a graph forecasting or graph temporal prediction or generation. So there are different terms, or dynamic graph prediction. So you can use different terms for this. So for example, dynamic graph prediction. Also, we can say generation, right? And you can use other terms like forecasting and other terms, okay? Cool. So this was the overview of, the general overview of how we formalize generative GNN tasks in a supervised way. And now I would like to cover the self-supervised or the unsupervised way of generating a graph. So this is, a different problem here that we're